Good morning, friends. Today we are going to start the experiment number 7, pump performance. So in this experiment we have a lot of experimentation. Just record the readings and do the calculation. So there are many calculation and experimentation is very small and very quick. So first, the pump running at constant speed to plot the pump characteristics curve, and pump running at variable speed to plot the system characteristic curves. So first we will do this number experiment number A, and B is a homework, or you can try at any other day, or it is a similar procedure, only the calculation of plotting the graph is different. How to write the objectives is very important. So first objective we are going to learn is to know the working of the equipment. So first is a working, how the centrifugal pump works, and why we are going to study to investigate the relation between number one, very important. We are going to investigate the relation between the various parameters involved in the pump terminology. The first is a head. What is meant by head? How we can find out? Number two, discharge. Directly we can get this from the equipment discharge, and it is denoted by, the head is denoted by H, discharge is denoted by Q. And number three, we are going to find the speed and torque on the pump. So this is very important. N and T we can directly record from the equipment. So number four, power input, and it is denoted by PI. Then next we are going to find power output, and that is also called as hydraulic power, PO, or P hydraulic. And last is your pump, and it is nothing but it is denoted by new pump. So these parameters we are going to find, how to find these parameters and how to calculate these values. And next objective is to find the values of these parameters. And number four, graph. So there are two types of graphs. One graph is a pump characteristics curve and system characteristics curve. Pump and system. So pump and system, how we can find this? Pump characteristic curves means a single pump working at constant speed, and system characteristics pumps, a single pump working at variable speed with a single valve opening position. And in pump characteristic curves, the speed is constant, and we are going to, the speed is constant, and we are going to vary the discharge. We are going to increase or decrease the volume flow rate, and this is at constant speed. And at variable speed, we are going to find Q and H. So if you change the speed of the pump, what is effect on Q and what is effect on Z? And we are going to plot the graph. That graph is called a system characteristics curve. And when pump is constant, and we are going to change the discharge by opening the valve 0%, 10%, 20%, 30%, 40%, 50%, 60%, and fully open. Then we can find out head, power, torque, efficiency, and this curve is called pump characteristic curve. So let us start the experiment and record the readings. And here we have two equipments. Number one equipment is a arm-feed multi-pump test rig. Here we have different types of pump, and we can find the performance of the pump, only performance of the pump at constant speed and variable speed. And for this experiment, you can refer my previous video. Now we'll go for another experiment, a GUNT, GUNT pump multi-pump test. Here we can do the pump performance also. There are two centrifugal pumps, choose P1 or P2, and we will find the head power input efficiency of that pump at constant at variable flow rate and constant speed. Same we can repeat the experiment with a variable speed, and we will plot the graph for series and parallel connection. We will do the series and parallel connection for two centrifugal pumps, and we'll plot the graph for different characteristics. So this multi-pump test trick, refer the manual. It is very important before. Now I am here to explain you how it works and not how it works and how to take the readings. I will explain it. If you are doing another experiment, refer the manual. So here I will explain this equipment. During the experimentation also I explain. So there are two pumps, P1 and P2. These two pumps are centrifugal pump, and here we can fix any another pump for testing purpose. And here this is a displacement pump or maybe a reciprocating pump. This is not a rotary pump. So this is a rotary, this is a rotary pump, and here we can analyze any outside pump. And this is another displacement pump, maybe a reciprocating pump, maybe a displacement pump, and this is a fixed. So now here we are going to use P1 or P2. So this is a inlet water. Here inlet water is stored, and this is a inlet pipe. So first in observation, we need to record the inlet pipe diameter for pump 1 or pump 2, which we are going to study. Then we need to record the pump diameter at outlet or outlet pump diameter. So this is DO, outlet diameter of the pump, inlet diameter of the pump, DI. This we need to record. Then then the 27 is the pressure sensor, 25 is this is a pressure sensor at outlet, and we can measure the PO, P for pressure, small p, O for outlet for pump number 1, and this is PO for pump number 2. And here this is a inlet pressure sensor, and we can measure here PI for pump 1, So this is observation, and all these, and we need a properties of the water. We can take it from the table. So observation tables. In observation we need to record. We need to select pump 1, and we will not select this pump 2, or another student will do on pump 2. So here we need to record the pump diameter. It is a 50 millimeter. The diameter of delivery side is 32. We need to record it, and we need to record from the manual the distance of the pump, the height of the pump from the water level. From this height is called Z, ZI, and the outlet height of the pump, from this is called ZO. So we need to record this from the equipment manual. From the water level and outlet height from the pump is, the difference is 0.21, which is used in Bernoulli's equation, and these properties of water. So record the readings.
Yes. So first connect this video, connect this to power source. Okay. So there is no chance of any wrong connection, because when you plug and go and no way. Okay. Then next, start the computer, or just keep the computer on. Then make this switch on. Okay. Here you will see this water. Make sure there is a water level. Okay, now we are going to choose the pump 1. Okay, so this is for pump 1 and this will open in this direction. So pump 1 is here, pump 2 to 5 is here. So first I will check the characteristics of pump 1. So increase the speed of pump 1 from here. Okay, so first make the pump on. This is pump on. Then increase the speed of pump 1 from here. So you can see, and select this speed as 1200 or 1300. It is given to you. It is your choice. So make this increase slowly. So before that, make this on. Fully open first. Okay. Then I will make the speed now to 1300 or 1100 is given to me. Try to make it a round figure 1400. Yes, 1400. So here we will get discharge, here we will get torque, here pressure at the inlet, pressure at the outlet. So open your observation table and record these readings. Okay, then I can open this first reading 0 means fully open. Then I will decrease this slowly, 15, then measure all the readings, then 30, measure all the readings, then 40, measure all the readings, 60, measure all the readings. Understand? Very simple. Now I will make it again fully open and take the readings. So make the speed 0. Make the speed 0. Close this wall and switch off. Okay, and switch off. Now we will do the series and parallel connection. Okay, so I will explain the series and parallel connection. So this is for pump 1 and this is for pump 2. P1 and P2 is written here. So if I make it close and if I make it both open, so water is coming here and pumping here and merging here. So this is called parallel. Okay, so this is closed and both V1 and V2 is open. So it is a parallel. Okay, then I will make this close. I will make this open. Now water is coming from here. It is pumped here, here. It is mixed with inlet and then it is going here. So series. Okay. So this water is velocity is increased here also again and here also again. So this keep it V6 open and V1 close, V2 open and all are open. So this is called series. Okay. So at the beginning I will start make the switch on. Okay. Then start pump 1 and pump 2. Okay, keep this first parallel. I will close it. So this is a parallel connection. Okay, then increase the speed and keep the speed same. Speed 1 and this. Okay, keep the speed both same by both finger or you can play later on. So I will make it 1400 again same, so that we can compare with first result. It's making noise now. Long time I started. Yes, this is 1400. Yes, 1440. So no need exact, must be exact. Okay. Now this water here, before it was 90 or something.
Yes, 90.
Now see double. And here you can calculate and then you can plot the graph. What is the effect on head, old one and new one. Okay, with series and parallel you can compare the result. So this is first reading. Take the picture and write in the series. First is here, second parallel connection. Okay, so take this picture. Yes, now make it 60 opening, 60, 60. Yes. And now wait for 2-3 minutes and record these readings. Yes, 62, no variation. Take this now. 61. Yeah, take this picture. Now last reading, make it 75 opening, 75% closing. And the V6 is closed, so this is a parallel, and you can record these readings. Yeah, flow rate is very small. Okay, at the end, make it fully open. Show the next part. Yes, and now we are going to make it series. Okay, we are going to make it series. Now V6 should be open and V1 should be closed. Yes. Yeah, first open the V6. Yes, and close the V1. Yes, now this is a series connection, and now measure the pressure, core pressure for pump 1 inlet outlet, for pump 2 inlet outlet, and it is fully open. Yes, now record these readings. Yes, now change the valve position V2 to 15. Yes. Yes, wait. It becomes 11. 10. Yes, record it. Now goes on, continue 30, 40, 60, 75 to finish the experiment.
So change the position of wall to 0%, 50%, 30%, 45%, 60%, and record the discharge, record the inlet pressure, record the outlet pressure, record the speed, and record the torque. And then change the wall position to 15 degrees in 15% opening and record all these readings. Okay, so these readings are recorded, and now the pump characteristics for pump 1 or pump 2. Keep the valve open 100% and vary the speed. So we didn't do this experiment. This is a homework or the extra work which may be asked in exam, but you have to do yourself. So this is a self-learning skill. So here vary the speed, keep the valve opening 100% valve open, vary the speed and record all this. So this work is for you only. And then we will connect. So now series and parallel connection between pump P1 and P2. So here P1 and P2. So water is flowing in this direction. The water is flowing in this direction upwards. So like this. So here if you start the pump 1, so we need to make this wall close. So water will take turn like this and it will go to the as a inlet, and then this is outlet open. So we can control from here like this, we can control. So this is single outlet and there are 2 inlet. So this pressure 1 and this is pressure 2, inlet pressure for pump 1 and inlet pressure for pump 2. We can take the average, and this is the outlet pressure, and then we can do the sample calculation. So this we need to keep the wall V7 open, V7 open and V1 close. So we get the series connection and we'll do. Similarly, change the wall position 10, 20, 30, 40% and then record the readings. Then keep this wall close, V7 close, keep this closed like this, keep this closed like this, and open this wall. Okay, and then water will flow like this, water will flow like this. For this there are two outlet and two inlet individually, two pumps are working individually, and but the Q is combined here in parallel series. So here inlet pressure for pump 1 and pump 2 we need to take the average. The outlet pressure for pump 1 and pump 2 we need to take the average for sample calculation, and then we will do the rest of the calculation. So record these readings in the series and parallel connection. Series pump connection, pump P1 P2. So we are going to maintain the speed constant. So sorry, this is a 1400 RPM, 1400 RPM. So record, change the valve position to 0, 15, 30, 40. Then volume for it, we can record it. Pressure for pump, inlet pressure for pump, inlet pressure for pump 2, pump 1, inlet pressure for pump 1, outlet pressure for pump 1, inlet pressure for pump 2, outlet pressure for pump 2. So this is the only observation. We are not going to measure speed, RPM, torque, anything. Here we are not going to find the performance. We are only finding H, head, pressure head. So same for parallel. So this is a wall position, discharge and pressure at P1 inlet, pressure at P1 outlet, which is a inlet for pump 2, and this is a pressure inlet for pump 2 and pressure outlet. So we need to record all four pressures. Now we will do the sample calculation for reading number 1 and prepare the Excel file for another calculation, or you can do it sample calculations. First, our objective is to find out head. What we need to find out head, what we need to apply a Bernoulli's equation. Bernoulli's equation at inlet and outlet, we can apply it, and it will be as P by gamma at inlet. Gamma is a specific weight of the water. Then this is called pressure energy. Then kinetic energy is Vi square by 2G plus Z is equal to pressure at outlet over gamma plus velocity at outlet. This is the inlet, and 2G plus Z. This is inlet and this is outlet. And here the head loss due to friction, or head, it is not loss, it is a gain. So this is a head is here. So our objective is to find out head. In our experiment, we measured pressure. We need to find velocity. It is Zi and Z is given to you. Pressure we measured. Now we need to find velocity. So what is velocity? Velocity is nothing but Q by area. So here we have Q, and area we need to find. And what is area? Area is equal to pi by 4 d square. So here we have inlet diameter and outlet diameter. By knowing this, we can calculate H. Once we know the head, we can find out power input is nothing but 2 pi nt by 60. Okay, so here RPM we measured, torque we measured, we can find out power input very easily. Number 1, number 2. Number 3, we need to find hydraulic power, that is output power, and this is nothing but gamma Q EH. So here we just found out Q we measured, gamma is a property. So we can find out hydraulic property. And as last step, we need to find is the efficiency of the pump is given by output by input. So what is the output? Output is a hydraulic power, and input is a electric motor power input. We can find out the efficiency. So this is the flow chart, and now try to find all the values. Now in sample calculation, the first step, now I told you flow chart. So first I need to find velocity. For velocity, what I need to find the area. So Flow area at inlet is given by AI is equal to pi by 4 di square. So put the values pi by 4. Di is the input diameter of the pump and it is given to you 50 milli. Milli is not allowed, 10 to the power minus 3 square. Okay, and here you will get the area 1.9635, write 4 digits, 10 to the power minus 3 meter square. Then number 2, I will find the flow area at outlet of the pump into 32, as I wrote in the observation table, 32 meter square, 0.8043 into 10 to the power minus 3 meter square. Flow velocity at inlet and outlet is given by Vi is equal to Q divided by AI and VO is equal to Q divided by AO. So put the values, the discharge I told you in observation table, yes, 98. Discharge is 98. What is the unit? Liter per minute. Liter per minute divided by area. What is area? 1.9635 into 10 to the power minus 3 meter square. So this is not a SI unit. We need to use a basic SI unit as I am explaining from the beginning. So 98 into 10 to the power minus 3 meter cube. So 1 liter is 10 to the power minus 3 meter cube. Okay, so I replace liter by 10 to the power minus 3, and now minute 60 second, I replace minute by 60 second. Here don't memorize, divide or multiply. Okay, replace, and here as it is 1.9635 into 10 to the power minus 3 meter square. Now here you will get answer. See, this meter square and this meter cube get cancelled, only remaining meter and meter per second. So your answer is meter per second. And how much VI? 0.8318 meter at outlet. 0.8043 into 10 to the power minus 3 meter square, and you will get the answer 2.0308 meter per second. Once we know the velocity at inlet and outlet, we will go for the number 4, head. How I can find the head? By Bernoulli's equation. Number 4, this is important. So number 4, so this is a energy conservation principle, law of conservation of energy. Energy neither be created nor be destroyed. It can flow from inlet to outlet, one place to another place. So this is the energy at inlet is equal to energy at outlet, the pressure energy at outlet. We have all the values and we will find the yet. So head pressure head is given by PO minus PI by gamma plus VO square minus VI square divided by 2G plus ZO minus ZI. So this is the final formula, and while writing the formula, take care of the unit and see the unit. I will explain with the unit here, and this will be very good for understanding what is the unit of pressure. Newton per meter square. No bar is allowed here. Okay. Gamma. What is the specific weight? Gamma is nothing but rho g. What is the unit of the density? Kilogram per meter cube. What is gravity? Meter per second square. Kg meter per second square is called Newton. Remember this, Newton per meter cube and Newton per meter square. The Newton per meter square get cancel, and this meter and the square get cancelled, then unit is meter. So the unit of the Bernoulli's equation is a this question asked in interview. The pressure energy, it is a head, pressure head is expressed in meter, and the Bernoulli's equation is expressed in meters of water, meters of fluid, and this is a energy, unit of the energy, pressure energy. Now for plus velocity, kinetic energy. Kinetic energy, what is the unit of velocity? Meter square second square, meter per second, and square is meter square second square. 2, this number. And what is the unit of gravity? Meter per second square. See, simple. Meter per second square get cancelled. What is remaining? Meter. And this potential energy, it is given to you 2.1 meter. So all the units are meter. This equation is a dimensionally homogeneous. H is equal to, now pressure at inlet is 0.01 bar and outlet is 0.06 bar. The pressure at outlet is 0.06 bar. Bar is not allowed, 10 to the power 5. So this is a Pascal and should be in basic SI unit, primary SI unit. Minus, what is PI? Suction pressure, it is given as minus suction. So it is a minus 0.11 into 10 to the power 5 divided by the density of water is given as a property 997.29, and the gravity 9.81, use 81, plus velocity is 2.0308 square minus 0.8318 square, as we calculated before, into 2.981. So here we calculated velocity and we are going to put this velocity plus 0.21 meter is the potential head, and here we will get the total head developed by the pump. H is equal to 2.1226 meters of water. Now we'll go for hydraulic power output. Number 5 is given by PO or P hydraulic, capital, not pressure. Don't confuse this, capital P, small p for pressure, and capital P for power, and it is given by gamma QH. I will explain the unit. Explaining with unit is very important to understand the formula, to find out the mistake. So specific weight of the water is rho g. Rho g. What is the gamma unit of specific weight? Newton per meter cube. Into what is the discharge? What is the volume flow rate? Volume. Volume means meter cube. Rate means second. Volume flow rate. And what is the head? Meter. This meter cube get cancelled. Newton meter is called joules per second, and joules per second is called watt. The unit of power is watt. Put the values. So gamma is rho g 997.29 into 9.81. Okay, so this is a specific weight. Into discharge, as I explained before, discharge is 98 liter per minute into 10 to the power minus 3 divided by 60, multiply by head. How much head we calculated here now? So multiply by 2.1226. So here you will get the answer 33.918 watts power output of the pump. Now next we will go for 6, power input to pump. We can calculate, as we study in another courses also, electrical technology or another courses, power input for electric motor is given by 2 pi nt divided by 60, where n is speed, revolution per second. Here it is very important, revolution per second, because we divided by, if you don't divide it by 60, it is rpm, and torque is in newton meter. So revolution is no number, so Newton meter is nothing but Newton meter is nothing but joules second as it is, and you will get watts. So put the values 2 pi. So RPM is 1400 into torque is is 0.61 divided by 60 for second. Okay, so we'll get this 89.4307 watts. So once we know power input and power output, we can go for number 7, pump efficiency. It is denoted by nu, and P for pump, it is a suffix. Output by input. So what is the output? Output is a hydraulic power, P hydraulic, HYD, and P input. P hydraulic is 33.918918 divided by power input is 89.4307. So you will get a fraction. So write first fraction 0.3793 and multiply in mind by 137.93. So 100 means 2 decimal places move here, percent. So this is the pump efficiency. So repeat the calculation for another reading, okay, and then we'll move to the graph. So this finish first part. Now next part is two pumps, P1 and P2. P for pump now are connected in series. Now here our target is to find head only. So to find out head, we need to find velocity again. And for velocity, we need a area. Area we already found out. Now we have different discharge. So we'll find out velocity at inlet and outlet V and VO. First step, the discharge, it is now pumps are connected in series. The discharge is 112 liter per minute. I told you, convert it. Replace liter 10 to the power minus 3 meter cube divided by 60 seconds. Replace minute by 60 seconds, and here you will get the number 1.8667 meter cube per second. So this is a discharge volume flow rate. Now we have area at inlet 1.9635 into 10 to the power minus 3 meter square. Area at outlet already we calculated 0.8043 meter square. Now I can find out velocity at inlet and outlet. Vi is equal to Q by AI. No need formula, so I can write directly. So 1.8667 into 10 to the power minus 3 divided by area is 1.9635 into 10 to the power minus 2 is equal to 0.9507 meter per second. Then VO is equal to Q by AO. So same QO. Outlet is 0.8043 into 10 to the power minus 3 meter square. I will get the velocity 2.321 meter per second. Now I have VIVO. Now I can apply the Bernoulli's equation. Total head by Bernoulli's equation. Now writing equation is very important. Before that we need to understand the diagram. So how the pumps are connected in series. So this is pump number 2 and this is pump number 1. So this is inlet for pump, and I can measure the pressure, pump pressure at inlet for 1, and this is a outlet pressure, PO, outlet pressure for pump 1. Now this is a inlet for the pump 2 and this is outlet for the pump, and it goes to outlet. So in series connection, this outlet is given to inlet. So here the pressure is pressure for pump inlet for pump 2. So here the pressure is pressure at outlet for pump 2. This is a main inlet and this is a main outlet. So these two pressures are useless. So this is not used in the calculation. So I can write the equation. The head Bernoulli's equation, head is given by PO2 outlet pressure minus inlet pressure PI1 divided by gamma plus velocity again VO2 square minus Vi1 square divided by 2. So here velocity is Vi1. Here velocity is VO2 plus ZO minus ZI. So put the values and we'll get the answer. So PO and PIO1. So we need to write this from the observation. So this is PI inlet and this is PO2 inlet outlet, PO outlet at the pump 2. So this is required. Okay, and this is discharge. So we'll write this in the equation. So H is equal to pressure at outlet is 0.07. It is bar Newton per meter square minus of minus 0.12 into 10 to the power 5 divided by gamma 997.29 into 9.81 Newton per meter square plus velocity at outlet. So here the velocity already we calculated. This is the velocity and this is, we will put this value 2.321 square minus 0.9507 square divided by 2 into 9.81 plus the potential head 2.1, and you will get the total head for series connection is equal to 2.3806 meter. So this is same, no need to calculate power and torque input efficiency, nothing. Now repeat the procedure for all readings. And now third part is P1 and P2 pump connected in parallel. So Bernoulli, before that we will understand this is pump 2 and this is pump 1. Pressure, input pressure for pump 1, output pressure for pump 1. So here input pressure for pump 2. Here output pressure for pump 2. So this will mix together. So here pumps are in work individually and the output are connected together. So while applying the Bernoulli's equation, we need to find average of these two pressure and average of these two pressure. So output pressure for the pump 1 and 2. Output pressure of pump 2 plus output pressure of 1 divided by 2. So this is called average pressure. And input pressure for 1 and 2. The input pressure for pump 2 plus input pressure for pump 1 by 2. PO outlet pressure for the system 1 and 2 is equal to 0.10 plus 0.13 divided by 2. So here I will get 0.115 into 10 to the power 5 Newton per meter square. So I converted bar into Pascal. Then input pressure for 1 and 2 is equal to, so make average of inlet pressure minus 0.10 plus 0.10, sorry, minus, both are minus, so minus minus minus. Okay, so divided by 2, both pressure are suction, so we can make the average of minus and it will be a minus 0.10 into 10 to the power 5 Newton per meter square. So similarly, I need to find the average velocity. For average velocity, I need a discharge is equal to, it is for series and so this is a parallel connection. So I will go for parallel connection. Yeah, this is parallel discharge is 123. 123 liter per minute. Q is equal to 123 into 10 to the power minus 3 divided by 60 meter cube per second. So it will be 2.05 into 10 to the power minus 3 meter cube per second. Okay, so once we know the discharge, the area of the pipe is same, so no need to calculate. I will put directly value, so I can find velocity at inlet pump 1 is equal to velocity at inlet for pump 2 is equal to same Q by AI, and velocity at outlet for pump 1 is equal to velocity at outlet for pump 2 is equal to Q by area at outlet. So just put the values and you will get the velocity. So Q is equal to 2.05 into 10 to the power minus 3 and area I is 1.9635 into 10 to the power minus 3 is equal to and here I will get 2.05 into 10 to the power minus 3 divided by area is 0.8043 into 10 to the power minus 3. Here I want to tell you the inlet area is always more and outlet area is always less to avoid cavitation. This question asked in interview, remember. So the velocity at inlet is 1.044 meter per second and velocity at outlet is 2.5488 meter per second. So velocity at outlet is more, but area is small. Area is small, that's why velocity is more. So I know the velocity, I know the pressure, average pressure. I can find head number 3. The head for parallel connection is given by H is equal to, write the equation now from the diagram. So pressure at outlet PO for pump 1 and 2 minus pressure at inlet pressure 1 to 2 gamma plus velocity at outlet 1 to square minus velocity at inlet 1 to 2 square divided by 2g plus ZO minus ZI. So as I calculated pressure here, you can see here the pressure is 0.15 and this velocity is 2.5 and I will enter this value in this equation. The total head by Bernoulli's equation, we can put the value directly here. 0.115 into 10 to the power minus 5, plus 5 minus of minus 0.10 into 10 to the power 5 divided by 997.29 into 9.81 plus the velocity as above 2.5488 square minus 1.044 square divided by 2 into 9.81 plus 0.21. H is equal to 2.6832 meter. Okay. So this finish the calculation. Now do the calculation for all the readings and we'll go to plot the graph. So how to do the calculation by Excel, I will explain here. See the pump characteristic centrifugal pump, I selected P1 and all the data is written here. The observation table is written here. The calculation, so this is discharge. Discharge is this divided by 60,000, that is 10 to the power 3 minus 3 divided by 60, it comes here. Meter here, Bernoulli's equation, I put Bernoulli's equation, this minus this, everything, and this is a calculation table. For series and pump, same way we did it here and same way we did it here. So this is sample calculation how to complete this table, and we can plot the graph here, but we need to plot the graph manually, not by Excel. So this graph is called the pump characteristics curve. Pump characteristic curve is plotted between the discharge Q in meter cube per second versus the head H in meter, okay. And on another axis we can plot efficiency. You can write here efficiency also in percentage. So first we need to decide this axes and then you need to write the scale. So scale is very important. For graph more than 50% marks are assigned for labeling the axes and writing the scale. So on the scale, first on x-axis I will write x-axis, I will write 10 lines. See here there are 10 lines, so I will write 10 lines is equal to, or I can write one line or 10 line I can write by looking into the graph. So I need to find the discharge, so I will check the discharge, the calculation table, pump characteristics for pump P1, and this is no P2. Okay, so this is a discharge. So here discharge minus 3 minus 3 minus 3 minus 3 minus 4. So instead of minus 4 I will write here 51667 into 10 to the power minus 3 and I will make it 0.5. So what is the scale? 1.6, 1.63. So I will consider here two digit, 1.61, 1.50, 1.10, 10, 50, 60, 63. So I can start from 0 0.5, 1, 1.5, okay, into 10 to the power minus 3. So this is for discharge. Now I will go for head. Head is starting from 2.1, 2.12, 2.11, 2.12, 2.11. So maximum is 2.11. So I will start from 2.12 here, 2 digit 12 and 2 point around 3. Okay. So here no problem. Efficiency starting from 24 means I can start from 20 and up to 50. Okay. So this we need to decide first and then write the scale. Okay, so discharge, as discharge I told you it is varying from, so here 0 0.5, 0 0.75, 1, 1.25, 0.25 I'm increasing, here 1.5, here 1.75. What is the maximum? 1.6. Okay, so 1.6 is near about here. So it is chance. It's okay now. This is into. Don't forget this 10 to the power minus 3. Now we'll go for head. Head is varying from 2 to 3. So I will start. This is 2. So 2.2, 2.4, 2.6, 2.8. Now efficiency is varying from 24 to maximum 40, 24 to maximum 42, 20, 25, 30, 35, 40, here 45. So this is in percentage I wrote. So here I need to write the scale. 10 lines is equal to, on x-axis 10 lines is equal to 0.25 into 10 to the power minus 3 meter cube per second, the scale. And on y-axis 10 lines is equal to zero point 0.2 meters of water, and another 10 lines is equal to 5% of efficiency. Scale is having maximum marks. Writing scale, labeling x-axis, labeling y-axis, labeling another axis, and now let us start plotting graph. 0 0.5. So I will little change the scale. 0 point. I am starting from 0 0.5. Doesn't no need to start from 0 0. So you can start from any. So this is 0 0.5. 0 0.7. I will change this also one line. So means divided by 10. So here one line is equal to 0.02 meter. So this is 0.5254 correct now. 02. So 72, 70. So this will become 0 point by 2 means this will be 9. Okay. 1.1, 1.3, 1.5, 1.8 into 10 to the power minus 3 meter cube per second. See, this is good scale I found. At least we need to think a lot of on that. So first is 0.5 to 1.10. So like that 1.10. Now I will find this exactly. So 52, the first line is 52.52. Okay. Second line is 1.1. This is correct. 1.10. 1.10 correct. Now 1.5 is here. 1.6263, 1.62 and 63. So 1.6. So 1.6 is here. 1.62 and 63. So very close. 62, 63. This is 62 and this is in between 63. Okay, so these are the points. Now I will go for head. Now head is 2.98, so around 3. So I will make it 3 and 2.64. 2.3 and 2.64. 2.3 for first, 2.3 is here. So this is first line, this point. Okay. Then next reading is here 1.1. What is 1.1? What is the head for 1.1? 2.64. 1.1, 2.64, 2.64, 0.64. This is 2.7. So this 2.1.1. This is 2.64 in between here. Okay. Then next 2.3, 2.3 for 1.5. 1.5, 2.3, 2.3. This is 4 and this is 3. 2.3 here. 2.3. Sorry, for zero point 0.5 it is 3. For zero point 0.5 it is 3, not this point. So I will erase this first point. For 0.52 it is 2.98, near about 3 here. Yes, first, second, third finish. Now we'll 1, 2, 3 finish. Now 2.1, 2.12, 1.6, 1.6. The next line is 1.6 here, and the head is how much? 2.1, 2.1, 2.1 here, 2.1 here, 2.1, and last 2.12, 2.12, 2.12, 12 little here. Okay, so draw the smooth curve, and draw the smooth curve from this. This is increasing here. Okay, it will be like this, or maybe. Okay, next we will plot the curve for efficiency. So here round figure I will make it 25, 37, 42, then 41, and then 38. So first 25, 37. So 25% for this line, 25% is here. So change the color to blue. So first line 25%, first point. Then second point, second 37, 42. 37, second line is here. 37, 35, 37 is somewhere here. 37.5 is somewhere here. Then 37, okay. 42, 41. 42, 42 is on this third line. 42, so somewhere 42. Then 41, 41 and 38. 41, this line 41, 40, 41, two lines. Okay. So here one line is equal to 2%, 2.5%. 2.5%. Okay, so 21, 25 means the difference is 5 divided by 10, 0.5, 0.5. One line is 0.5, two line is 1, two line is 1, correct. Two line is 1 for efficiency. And next is last efficiency is 38. The last efficiency is 38 on the second line. 38, 35, 36, 37, 38. Again two lines, 36, 37, 38. So this is the efficiency curve. Yes, very nice. And this point is called operating point for pump 1, is the optimum point. So similarly, we can plot the second graph, only one H and Q for series pump, and for parallel pump you will get like this curve, two curves. Similarly, we can plot it, and from this graph you can write the conclusion. The efficiency of the pump will be optimum at this point and at this point. Understand? So measure this head. The head will be optimum and the efficiency will be optimum at the particular discharge. And that I didn't take the readings for. So there is a one more graph for, this is called a system characteristics, not pump. It is called a system characteristics. System characteristics for centrifugal pump or for all system. So speed is varying. So go on x-axis, sorry, discharge Q. Okay, and then here head. So Q and head, plot the graphs. So you will get the graph like this. So this is speed 1, speed 2, speed 3, speed 4, whatever. So this curve is called characteristics. So whenever you do this experiment, remember that you need to plot the graph between head and discharge, and when speed is changing. Got it? And for series and parallel we can plot similarly. Thank you very much.